Ladies and gentlemen, my name is Lukas Makevicius. I'm a research assistant at the Institute for Metal and Lightweight Structures of the University of Duisburg-Essen. And without further ado, I would like to start our presentation entitled Loss of Preload in Preloaded Bolted Connections over the Service Life. The results that will be presented here originated from the systematic investigations in the frame of the IGF research project with a very similar title of Loss of Preload of Fatigue-Loaded Preloaded Bolted Connections. These investigations were carried out by the Institute for Metal and Lightweight Structures of the University of Duisburg-Essen and our partners Fraunhofer Research Institution for Large Structures and Production Engineering in Rostock. The following overview gives you a brief idea of what you can expect over the next 12 to 13 minutes. I would like to start a presentation with a short introduction and a summary of the current normative regulations. Then the systematic investigations into preloaded bolted connections will be presented, including, of course, their results. Finally, the experimentally determined system reserves and preload losses will be considered regarding the required preload level, and I will finish this presentation with a short outlook and an acknowledgement. To start with, the bolted connections can be preloaded either for load-bearing capacity reasons, also known as target level 1 of preloading, or for serviceability reasons, in this case target level 2 of preloading. The slip-resistant connections and preloaded tension connections both rely on a specific preload level that is included in the design. Depending on the category of the connection, a sufficient preload level not only has to be achieved during the tightening method, but also has to be ensured over the whole service life of the structure. It is well known that preload losses due to different factors like setting effects, creep, cyclic loading may affect the level of preload, which means that their consideration during design and execution is necessary. The European standard EN 1090 Part 2 considers those preload losses quite simply. First of all, in case of slip-resistant connections of categories BC, the major potential preload losses are implicitly considered in the slip factor. Secondly, EN 1090 Part 2 states that the specified tightening methods implicitly cover 10% preload losses. Even though a realistic estimation of preload losses is vital for the structural safety, it can be seen that this is only possible to a very, very limited extent, and that systematic investigations into preload losses and the so-called system reserves are necessary in order to answer a couple of questions. First of all, can the defined tightening methods meet the 10% overshoot demand, and is it enough to cover preload losses? Secondly, how much over tightening is needed to ensure the required preload level over the service life of the structure? In terms of our research project, separate investigations into preloaded tension connections and slip-resistant connections were carried out. These investigations considered different clamping length ratios of 2 and 5, different surface treatments like grit-blasted surfaces or zinc spray metallized surfaces. Different bolting assemblies and tightening methods were used to determine the initial preload level, which in relation to the required preload level can also be seen as the so-called system reserves. Here, H3 bolting assemblies were tightened using a modified torque method and combined method. HR bolting assemblies were used in combination with direct tension indicators. Also, tension control bolts and lock bolts were investigated. The investigations were carried out in a couple of steps. First of all, the relaxation tests were conducted in order to determine the initial preload level and preload losses that result after that due to setting effects and creep, or as we call them, relaxation. These preload losses were then extrapolated to the intended service life of structures of 50 years. Once the main preload losses due to setting and creep occurred, tests with external cyclic loading were carried out in order to determine preload losses due to external cyclic loading, where the input loads were determined in terms of separate static tests. Finally, the preload losses due to cyclic loading were extrapolated to 2 billion cycles. These experimental results allowed an assessment of the remaining preload force over the service life, which was vital for a critical review of the normative regulations. The experimental approach is summarized on the following slide. First of all, the test specimens were preloaded by using different tightening procedures in order to determine the initial preload level and therefore the so-called system reserves. After that, relaxation test was carried out, and once the main preload losses due to setting and creep occurred, the same specimens were tested under the cyclic loading. In order to estimate the remaining preload level over the service life, both mean preload losses due to relaxation and cyclic loading were extrapolated to the intended service life of the structures and then subtracted from the mean system reserves due to different tightening methods. The experimental results of the investigations are graphically summarized in the chart on the right, in this case exemplarily for preloaded tension connections. At first, the experimentally determined system reserves as mean values are discussed. It can be seen that a system reserve of at least 10% has been reliably met by using combined method and tension control bolts, where combined method even showed system reserves of up to 36%. The modified torque method, according to the German guideline, the Das-Richtlinie 024, possessed system reserves of around 5 to 10%, but on the other hand was distinguished by high scattering of the initial preload values. The investigated direct tension indicators showed some high deficits of up to 15%. It must be mentioned, though, that these specific direct tension indicators also failed the suitability tests for preloading. Finally, the investigated lock bolts achieved the required preload level very precisely, but at the same time showed only minor system reserves for possible preload losses of up to 6%. For the next step, the determined system reserves are supplemented with preload losses due to setting effects and creep. As expected, higher preload losses could be determined for lower clamping length ratio. This, of course, can be attributed to higher pressures on the fang surfaces. The system reserve of 10% that should be implicitly covered by the given tightening procedures according to EN 1090 Part 2 has been achieved for grid blasted surfaces already. For these surfaces, also a retightening using modified method has been carried out, which showed a potential for a compensation of preload losses and consequently led to lower preload losses after that. In general, specimens with coated fang surfaces exceed the intended system reserve of 10%, where preload losses varied between 11 and 22% depending on the investigated surface treatment of the specimens. Finally, it can be seen that high surface pressures on the protrusions of direct tension indicators lead to preload losses of up to 18% at the grid blasted surface condition. The conducted tests with external cyclic loading showed that the main preload losses due to cyclic loading occur within the first load cycles. Regarding the preloaded tension connections with different clamping length ratios, it can be stated that the resulting preload losses either are negligible or remain within 6% after extrapolation to the intended service life, and therefore can be assumed as non-critical. Although it must be mentioned that the critical stress surfaces under the washers were not coated. Experimentally determined preload losses for slip-resistant connections remained within the range of 10%, depending on the investigated surface treatment and the considered stress ratio. Here it can be mentioned that fully reverse stresses, as can be seen here, seem to be more critical, with preload losses between 2 and 10% for the investigated surface treatments. Finally, given the experimentally determined system reserves and preload losses as mean values, the remaining preload level over the service life can be estimated. Investigated preloaded tension connections showed that only a combined method possesses enough system reserves for possible preload losses and even exceeds the required preload by approximately 12 to 20%. Deficits of 10 to 37% can be addressed to grid-blasted connections with lock bolts and direct tension indicators respectively, where connections with tension control bolts or connections preloaded using modified torque method in combination with a retightening lie within the range of the required preload level. This also only applies to the grid-blasted surface condition, which of course can be achieved by masking of the fairing surfaces plus surfaces under the bolt head and the washer. As mentioned before, preload losses due to setting effects and creep are generally covered by the extended creep test. In case of slip-resistant connections, additional preload losses due to cyclic loading for the investigated surface treatments seem to be uncritical. The observed results allow a critical review of current regulations and also provide a fundamental knowledge for the consideration of preload losses in the future. Of course, further experimental investigations are needed, in particular to increase the number of the tests and to consider other common surface treatments in steel construction, or for example to examine the influence of different preload levels on the slip factor and the load-bearing behavior of slip-resistant connections. These investigations are currently carried out in terms of 2 different IGF research projects that are also coordinated by the Institute for Metal and Lightweight Structures of the University of Duisburg-Essen. We wish to thank the German Federation of Industrial Research Associations and the Federal Ministry for Economic Affairs and Energy for funding this research project, and of course the industry partners for their massive support. I would like to thank you for your attention, and in case of any questions, please do not hesitate to contact us. Thank you very much.